Plant starch and glycogen, animal starch, are the most abundant dietary carbohydrates. Carbohydrates are long polymers of glucose. Digestion of starch begins in the mouth with salivary amylase, which is maximally active at about pH 7. Drag starch to amylase to begin. Amylase breaks starch down to the disaccharide maltose, to fragments of 3 glucose molecules called maltotriose, and to small branched fragments called limit dextrins. In our illustration, each hexagon represents a glucose molecule. The hexagons at branch points represent glucose-glucose links that are not hydrolyzed by amylase. Click a digestion product to continue. Amylase continues to work in the stomach until food is mixed with gastric juice and acidified. Acid denatures amylase. Pepsin begins the digestion of protein. Proteins are long polymers of amino acids. Pepsin is the only major digestive enzyme that is maximally active at acidic pH. Drag the protein to pepsin to begin. Pepsin cleaves proteins it bonds between the amino acids tyrosine and phenylalanine, producing peptide fragments and a small amount of individual amino acids. In this illustration, each circle represents an amino acid. Click a peptide to continue. Pepsin is active only in the stomach. When chyme is neutralized in the duodenum, pepsin is denatured. Most digestion and almost all absorption occurs in the small intestine. The pancreas supplies the digestive enzymes for most foodstuffs. Neither salivary amylase nor pepsin is essential for digestion. Pancreatic enzymes alone are adequate to digest carbohydrates and protein. There is little digestion of fat until it reaches the small intestine. Pancreatic lipase is essential for fat digestion. Without it, malabsorption of fat occurs. Humans lack digestive enzymes for the plant polysaccharide cellulose and some other complex carbohydrates. Drag a vegetable to the intestines. Vegetables and fruits are good sources of vitamins, minerals, and other nutrients. The indigestible polysaccharides contained in vegetables and fruits make up dietary fiber. Fiber increases bulk of the stool and promotes its timely movement through the colon. Click the intestine to observe salt and water absorption. Most of the salt and water that enter the GI tract are absorbed in the small intestine. Salt and water may be absorbed by transcellular transport through intestinal epithelial cells or by paracellular transport through leaky tight junctions between cells. Paracellular transport is passive and keeps the total osmolarity of the intestinal contents similar to the osmolarity of blood plasma. The carbohydrates that enter the small intestine for digestion include starch, its breakdown products from salivary amylase digestion, and the dietary disaccharides, sucrose, table sugar, lactose, milk sugar, and maltose, grain sugar. Drag starch to amylase to begin. Pancreatic amylase continues the breakdown of starch in the lumen. It is identical to salivary amylase and maximally active at about pH 7. Since only monosaccharides are absorbed, the breakdown products of starch and the disaccharides must be digested further. Brush border enzymes accomplish this job. Click an epithelial cell to continue. A brush border enzyme called glucoamylase that lies close to the sodium glucose cotransporter breaks down maltose and maltotriose. Drag maltotriose to its enzyme.
Alright, I'm not going to do that one. I'm going to go to the next slide.
Ingested proteins, peptides from pepsin digestion, proteins from sloughed cells, and enzymes enter the small intestine for digestion. Trypsin, chymotrypsin, and carboxypeptidase, the major pancreatic proteases, continue protein digestion in the lumen. These enzymes are maximally active at about pH 7. Drag a protein to trypsin to begin. Trypsin and chymotrypsin cleave proteins into smaller peptides and some single amino acids. Carboxypeptidase cleaves one amino acid at a time from the carboxyl end of a protein. Dipeptides and tripeptides as well as single amino acids are absorbed. Click an epithelial cell to continue. Triglycerides are the most abundant dietary fat. They are made from a glycerol molecule to which 3 fatty acids are attached. Fatty acids may be short, medium, or long chains of carbon and hydrogen. Almost all fat digestion occurs in the small intestine. Pancreatic lipase breaks down triglycerides. It is maximally active at about pH 7. Since fat is insoluble in water, it tends to aggregate in large drops, leaving little surface area for lipase to work. Segmentation in the small intestine breaks the large drops into smaller drops and disperses those drops throughout the chyme. Click the large fat globule.
Okay, so stopping there with the animated series, there is not much left I can say about that, but what I can say is that watching these videos helped a lot better than just looking at the picture that's in the book. I'm going to now show the picture that's in the book. Okay, so here we have a picture that is straight from our text, and it basically says the exact same thing. But now, you tell me, is it easier to understand it after watching a video, or sitting here when you're being introduced to this? Not introduced so much because we have had prior learning to it, but a lot of terms are newer. Some of the things, the processes of it are new to us. So is it easier to sit here and look at this and try to decipher what's going on, or to watch the video and actually to see the chains splitting, and to hear him talk about how the glucose is broken down, and then next talk about how the proteins are broken down, and then next talk about how the glycerides are broken down? To me, watching the videos and the animations were much easier than sitting here and trying to look at this picture. Although it is a good picture and gives full detail, it just doesn't quite do it for me.